Hello everyone, my name is Horace, and in this video we're going to be going through LeetCode number 39, combination sum. For this problem, we're given an array of distinct integers called candidates and a target integer called targets, and we have to return a list of all unique combinations of candidates where the chosen numbers sum to targets. The same number may be chosen from candidates an unlimited number of times. Two combinations are unique if the frequency of at least one of the chosen numbers is different. The test cases are generated such that the number of unique combinations that sum up to the target is less than 150 combinations for the given input. So basically what we need to kind of pay attention to is this second paragraph here. So if we have something like 1, 3, this is not unique to 3, 1. Okay, let's take a look at this example, and we can start by listing out all the combinations in a tree-like structure. So let's say we start at the top or the roots. Well, which are the combinations that we have from, let's say, an empty list? Well, we can either take a 2, we can take a 3, or we can take a 5 value. So let's say if we take a 2, we'll get a list with 2, a list with 3, and a list with the element 5. Then from each of these, we can take another choice. So let's say from 2, we can take 2, 3, or 5, so long as it's not greater than the target value. And if it is, we'll just return upwards in the tree. So let's say from 2, we can kind of branch out in 3 more directions. And we'll say we have 2, 2. We have 2, 3, and we have 2, 5. So kind of these are the options, and we would obviously continue that for the 3 and the 5. And I'll just show you one example of when we actually do reach the target. Let's say eventually from the 5, then we take a 3 value from the 5. So we'll get 5, 3. And as you can see, 5 plus 3 is going to be equal to 8. So this is a value that will reach the targets. So what is the problem with this approach? Well, the thing is, we'll actually end up getting duplicate combinations. So for example, let's take a look at this value here, 2, 3. And let's say we continue, since it's less than the target, which is 8, we can add another 3 value. So we can basically have 2, 2, 3 as one of the potential options, and there would be other options as well. And the thing is, eventually from this value of 3, we'll get 3, 2, 2. And as you can see, these are both equal, and they also both equal the target value. So as it was mentioned in the problem, they have to have a unique number in their frequencies. So as you can see, we have 2 2s and 1 3, and we have 1 3 and 2 2s. So these are identical, and we don't want to duplicate the values. So we have to find another approach to solve this problem. Okay, for this approach, what we're going to do is we're going to basically have 2 decisions, one where we take a particular value and one in which we don't. So one branch is basically strictly going to be values containing that element, and then the other branch is going to be the decision where we did not have any occurrence of that in the branch. And this is going to be a recursive algorithm, a DFS. So let's begin by starting at the roots, and we have 2 options if we start at, let's say, the beginning of the list. We can either take a 2 element or not. So we have 2 branches here, and we can either take a 2 or we can not take a 2. So at this point, we'll just keep it as an empty list. Again, from this point here, we can either take another 2 since it's less than the target, or we can not take a 2 from this point. So let's say we either take a 2 or we don't. So the left will be another 2 appended in the list, and here we'll just take this root value from this branch. Then what we can do is we can keep continuing this. So this is still less than the target, so we have 2, 2, 2, and then we take this value here, which is 2, 2. Then finally, we can basically get a value of 8. So this is going to be 4 2's on this side, and this one we'll just assume is 2, 2, 2. But since we already found a value here, we don't really need to continue this path. Then what we can do is we can kind of go back in the tree, and when we recurse, we'll kind of look at this path. And since we've exhausted all the 2's up until this point, we can add a 3. So in this case, we have the choice to either add a 3 or not add a 3. Then let's kind of make those decisions. So we have 2, 2, 3, or we have 2, 2. And if we continue down this path, we can either take another 3 or we can not take another 3. This will be 7 plus 3, which is 10, and that's going to be over the targets. So we'll kind of assume this path instead, and we can either take a 5 or not take a 5. So let's say we take a 5, then we'll have 4 plus 5, which is 9, and that means we can't go down that path either. And at this point, we can take a 3. So we can kind of take a look at the choices between taking a 3 and not taking a 3. So we get 2, 3, or we get 2. And if we take another 3, we'll get 8. So this is 2, 3, 3. And this is a valid combination to reach the target value. So currently we have 2 values. One is right here and another is right here. Now I'll just quicken this process up. There's going to be no more combinations resulting from this path such that they equal to the target value. So now we're kind of dealing with the empty list on this side. So since we didn't take a 2 at this point, we can either take a 3 or not take a 3, since it's the next in the list. So at this point, we'll take a 3 or not take a 3. So 3 is going to be here, and again, we'll keep a empty list. From 3, we can take another 3 or we can not take another 3. So 3, 3, then we have 3, and we can't take another 3. This will lead to 9, which is greater than 8, and that's greater than the target, so we kind of just end the recursion at that point. Then we take a look at this. Can we add a 5? Well, yes, we can. We can actually get 3, 5, or 3. So as you can see, this is another combination such that it equals to the target. This sum, 3 plus 5, is equal to 8. And I'll just stop the process here, but these are all the values and combinations such that they equal to the target value. And if we continue on this side, well, we would basically just search 5 and the empty list, and at this point we can no longer kind of go. This will be 10, and this is the end of the recursion. So this is kind of the process that we're going to be taking to solve this problem. And to keep track of kind of the values that we're going, we'll keep some pointer in the list, and this will kind of move as we complete the recursion and hit base cases where needed. The time complexity for this algorithm is going to be big O of 2 to the t, since we have exactly 2 decisions at each level. And let's say we had a 1 element, so that means we would kind of continue until the height of the target. So there would be basically target levels or in the tree to constitute for the height. So this is where this time complexity comes from. With that being said, we can go ahead and code this algorithm on LeetCode. Okay, we're on LeetCode and we can start writing the algorithm for this problem. So let's say we begin by declaring a result array, and this is kind of the value that we're going to be returning and kind of updating with the combination. So let's say result is just some empty list. Then we can define a DFS function, which is going to kind of recurse throughout. We'll keep a pointer depending on where we are in the list and kind of which values are available to use in the recursion. Then we'll keep kind of the current combination that we're at, so we can call this current. Then we can also have the total value instead of calculating the sum of the currents, so we'll just keep a total value. Then we need to declare our base cases for the DFS function. So let's say we have the total, which is equal to the target. That means we are done, but we also have to append the current combination, and that's stored in the current variable. So we can do results append cur, but we need to make sure that we're not kind of aliasing with the cur. So we'll just create a deep copy with .copy, and we'll just kind of keep updating the current combination as we need throughout the function. And after this, we can return. Since this is a base case, we can just exit out of that. Otherwise, what is going to happen is if the pointer that we have is greater than the length of the candidates. So that means we've kind of gone out of the bounds and we need to return from that. Also, we can just return when the total value is greater than the target value. There's no possible way that we can have a combination that is greater than the sum. There's no possible way we can have a sum of the combination greater than the target, so we can just return out of that, and so we don't continue going down a dead path. So the two cases I described are both I is greater than length of candidates, or the total is greater than the target. In either case, we want to just return and kind of exit the recursive function. Then what we want to do is basically we want to add whatever current element we're at. We want to call DFS with both the added value, so this is kind of when we're taking the element decision, and then we want to call DFS on the tree that we're not taking that element. So what that means is we're going to basically append first of all the values, so candidates I, then we want to call it on the left subtree, so DFS, we're going to basically go left, I is going to be cur, and then we want the total to just be candidates I. So this is kind of just adding the total value, and then we can pop basically the value since we appended it here. But if we go down the right tree, then we are not using that value. Then we can just call DFS with I plus 1, and this is very important since we've exhausted all the values of the current pointer. So we have to use I plus 1 here, and then cur, and then total. So this is kind of just straightforward. We are just following our explanation of the algorithm. Then this is actually it for the DFS function. So outside of the DFS function, we can just call it with a value of 0. So 0 is going to be the 0th index where it's pointing to. We can call it with a current of the empty array, and then we can call it with a total of 0. The sum of the empty list is 0. Finally, we can just return the result, and this will give us the updated value. We were updating the result in the base case while we're going through the DFS. So this should be the solution, so we can try and submit it and see if we get the correct answer. And as you can see, the code is accepted, and this is running in big O of 2 to the t time. So with that being said, hopefully this video helped you and you learned something, and I'll see you soon.